How does a CNN's receptive field evolve through layers? Imagine looking at a picture through a tiny window. That window shows only a small part of the image. Now, think about how your view expands as you open more windows or look through bigger ones. That's similar to how a convolutional neural network's receptive field grows as it processes data. In a convolutional neural network, each neuron in the first layer looks at a small patch of the input image. Usually, this patch is the size of the convolutional kernel, like 3 by 3 or 5 by 5 pixels. These neurons detect simple features such as edges or textures in that tiny area. It's like noticing a small line or a corner in a picture. When the data moves to the next layer, each neuron doesn't just see one small patch anymore. Instead, it combines information from multiple neurons in the previous layer. This means it can recognize bigger parts of the image, like a shape or a pattern. The receptive field gets larger because each neuron now responds to a bigger area of the original image. Adding more convolutional layers makes this process even more powerful. Each new layer increases the receptive field size. For example, stacking several layers with 3 by 3 kernels makes the neurons in the deeper layers see much larger portions of the input. It's like zooming out gradually to see more of the picture. Pooling layers also help the receptive field grow faster. When a pooling layer, like max pooling, reduces the size of the feature map, it effectively doubles the size of the receptive field. This is because pooling summarizes information over larger regions, making the network aware of bigger parts of the image more quickly. Dilated convolutions, or atrus convolutions, are another tool. They insert spaces between kernel elements, allowing the receptive field to expand without adding more parameters or losing resolution. This way, the network can see wider areas without making the model more complex. As the network gets deeper, the neurons can see larger and larger parts of the input. This helps the network understand complex shapes, objects, or scenes. In advanced architectures like ResNet or Inception, the receptive field can cover the entire image. This global view is essential for tasks like classifying images or segmenting objects. Understanding how the receptive field grows helps in designing better CNNs. For example, in image generation tools like DALL-E or Midjourney, large receptive fields help the AI understand the overall structure of an image while still capturing fine details. It's like having both a wide-angle lens and a zoom lens at the same time. So, to sum up, a CNN's receptive field starts small at the beginning. It expands through stacking convolutional layers, using pooling or strided convolutions, and employing dilation techniques. This growth allows the network to recognize simple features early on and more complex, broad patterns later, making it powerful for understanding and creating images.